Okay, so this is the section 3.4 video, and it's all about concavity. So first of all, we need to kind of talk about, you learned that the first derivative tells you if a function is increasing or decreasing. But if that's all the information we have, that doesn't give me a very good graph of the original. For example, I could say, well, suppose I have a graph that I know is increasing. Well, does it look like that? Or maybe I have a graph that I know is increasing, but maybe instead of kind of bending down like that one, maybe it does something like that. Those are two very different graphs. Or I might even say, well, suppose I have a graph that is always increasing, but maybe at first it's kind of bending up, and then as it keeps going, it's kind of bending down. So notice all three of those graphs are always increasing, but all three of them are very different graphs. So there really is more information to be known about a graph or any particular function. All right, so the second derivative gives us some information as well. Second derivative tells us about concavity, and really that's kind of how a graph bends. Now, I don't know if that is a good word for it. That's kind of my own word for it. So, for example, concave down is where it kind of bends down, and concave up is kind of where the graph is bending or opening up. So in order to determine the concavity of a function, it always comes from the second derivative. So increasing, decreasing comes from first derivative, but concave up or down comes from the second derivative. So a function is concave up when its second derivative is positive, and a function is concave down when its second derivative is negative. Well, so far, this looks a lot like what we did in 3.3. It's just that when the first derivative was positive, it told us increasing or decreasing, right? Or positive or negative. Well, if the second derivative is positive or negative, it tells us concave up or down. Now, a first derivative told us if you had a relative max or min. Well, we have similar points for the second derivative, but they are called points of inflection. Okay, so points of inflection occur when a function changes concavity. On this, it could either go, the function could either go from concave up to down or down to up. We don't specify certain kinds of points of inflection. They're just all called points of inflection. So if points of inflection occur when a function changes concavity, that means that the second derivative is changing sign. And again, it doesn't matter if the second derivative changes positive to negative or negative to positive. All of those are called points of inflection. Okay, so what I've done here is kind of put side by side the information we did from the first derivative compared to the information we're doing from the second derivative. So for the first derivative compared to the second derivative. So for a first derivative, we said find the critical numbers. Well, critical numbers are when the derivative is 0 or undefined, right? Well, for points of inflection, we're finding where the second derivative is 0 or undefined. Those are not called critical numbers. I don't know why. You're doing the same thing. You're just doing it for the second derivative. In fact, they don't really have a special name. It's just where the second derivative is 0 or undefined. For the first derivative, we looked at a number line for the first derivative. Well, guess what? Over here, when we're finding points of inflection, we're going to look at a number line for the second derivative. So we're doing the same thing. We're just doing it on the second derivative. We're still going to label if it's positive or negative, just like we did on the first derivative. And then this time when we start labeling, whereas the original function being increasing or decreasing from the first derivative, the original function is either going to be concave up or down, and it's also going to tell us about points of inflection. Okay, so here's how it works. Look at my example. It says determine the intervals where the function is concave up and concave down and find all points of inflection. So since they mentioned concavity and points of inflection, I'm not going to stop at the first derivative. I'm going to go straight to the second derivative. So I'm going to say, okay, the first derivative is going to be negative 15x to the fourth plus 15x squared. And since I want to find where the second derivative, right, is 0 or undefined, I need to go to my second derivative. So the second derivative is going to be negative 60x cubed plus 30x. Okay, well, first of all, I can tell, since this is a polynomial, it's never going to be undefined. But I can set it equal to 0. I think what I'll do is factor out a negative 30x. And if I do that, I'm going to have positive 2x squared. Check my math here. And then minus 1. So that means, and again, we don't call them critical numbers, so I'm just simply going to say second derivative is 0 at x equals 0, but also when that parenthesis equals 0, right? So, and, well, what's going to make 2x squared minus 1 equal 0? Let's see, 2x squared would equal 1, x squared would equal 1/2. And so x is going to be plus or minus the square root of 1/2. And I don't even care about simplifying that. I mean, I know it's going to be some small decimal number, right? But good enough. So, and plus or minus square root of 1/2. And probably a lot of you could tell that without actually writing this out. So that part is kind of up to you if you want to write that out or not. So basically, I have 3 points where the second derivative is 0. So we set up our number line and we label it as the second derivative. So here's my 0, here's the negative square root of 1/2, and here's the positive square root of 1/2. Remember, I don't really care what that number is. I know it's a small decimal number, and that's good enough. So on this one, since the second derivative is a polynomial, I don't need to pick test points. I could think about end behavior. So the second derivative is a cubic, right? So odd degree with a negative leading coefficient. So doesn't that mean it's going to be coming down from the left and heading down towards the right? There's my end behavior. Notice neither of these factors has an even exponent. That does not have an even exponent. And you may be saying, oh, well, but the x squared does. Yeah, but the factor is the entire parenthesis. And the parenthesis right here has an exponent of 1. So that means nothing's going to bounce. I'm just going to pass through right there at the negative square root. I'm going to come back and pass through at 0. I'm going to come back and pass through. So this is my rough sketch of the second derivative. And so remember, I can say that the second derivative is positive in this first interval because the second derivative graph is above the x-axis. And then the second derivative is negative in this interval because the graph is below. Then the second derivative goes back to positive. And then the second derivative goes back to negative. So again, we're not looking at whether or not the second derivative is increasing or decreasing. We're looking at, is it above or below the x-axis? So I'm going to kind of get rid of this just because I don't want you to get confused thinking about increasing or decreasing. I only needed it to label positives and negatives. Okay, so now in order to give my specific information, I know that the original function, right, is going to start by being concave up, right, because the second derivative is positive. Then it's going to change to being concave down in that middle interval. Then it's going to go back to concave up, and then it's going to go to concave down. Now again, if I were writing this formally on a test, I would actually write the specific intervals. I would say it's concave up from negative infinity to negative square root of 1/2. Or it's concave up from 0 to square root of 1/2. Okay? And so I'm going to have points of inflection at x equals, well, doesn't the second derivative change sign at all of those? So at x equals 0 and plus or minus square root of 1/2. Again, if I was writing this formally on a test, I would say because the second derivative changes sign. You don't want to just say changes from positive to negative because only some of them are changing positive to negative. Other ones are changing negative to positive. So it's okay to say it generically and just say changes sign. Okay, so hopefully what you can tell is we did all the exact same steps that we did before. We're just doing them on the second derivative and therefore labeling them differently, the final answers. Okay, so that's one thing that you'll have to do in the homework is just go through and find the second derivative and determine positive or negative. But then the whole point of now that we know both first derivative information and second derivative information, we can put it all together and kind of come up with a rough sketch of the graph of a function. Remember, these are no calculator. So I may not know what the function looks like. I'm going to use the first derivative and second derivative information to figure that out. Okay, so let's say we're given all of this information, and I want to kind of put it all together to sketch the graph of f. Well, I always start with any specific points that I know. Okay, so this means I have the ordered pair 0, 0. This means I have the ordered pair 1, 1. Okay, and then it says the derivative at 0 is undefined. Well, if the derivative is undefined, that must mean the critical number is 0. So that's why they put a 0 right here on the first derivative number line. And then over here it says the derivative equals 0 at 1. Well, if the derivative equals 0, doesn't that mean that it's a critical number? So again, that's why they put on the first derivative number line, they put a 1. So they're marking these on the derivative. They've done the analysis. They told me that the derivative changes from negative to positive to negative. So what does that tell me about the original function? Well, doesn't that mean it goes from decreasing to increasing to decreasing? So if I go over here to my graph, before I get to x equals 0, I know my graph is decreasing towards that point. And then between 0 and 1, I know my function is increasing, right? So I'm going up to get to that next point. And then from 1 on out, I know my function is decreasing. So that gives me some direction. But now I'm going to look at the second derivative to give it a little bit more definition. So the second derivative is negative until I get to 0. That means until I get to 0, I need to kind of bend it so that it looks concave down. But when you bend it, be careful because I want it to still be decreasing. If you were to bend it too much and do something like that for concave down, now it's not decreasing the whole time, right? So I need to take off that little piece over there. So, okay, until I get to 0, it's concave down. And then this says from 0 on out, it's also concave down. Notice up here how it said the derivative was undefined at 0. Well, what does it look like on a graph if the derivative is undefined? Doesn't that mean there's a sharp turn? So that must mean there's a sharp turn right here at 0. So now do you see the second part of my graph is concave down also? And notice right here, if the first derivative is 0, isn't that where you have a nice smooth transition curve through the point? So that would be a rough sketch of the graph if you put both the first derivative and second derivative information together. Okay, this next part, I gotta be honest, it took me a long time to kind of get this stuff worked out in my head. This next part, you guys that are physics people, you're probably much better at this because you've probably already been working with position, velocity, and acceleration graphs. And essentially that's what we're doing. We just don't title them that. Okay, so the first part says, what if I give you the graph of the derivative? Okay, so just so that I can call it something, I'll call this one number 1. So I'm looking at the graph of the derivative. You physics people, that's like saying, hey, this is a velocity graph. Okay, and then it says, I want to sketch the graph of the original. So again, you physics people, that's like saying, hey, if this is the velocity graph, can you sketch the position graph? Or some of your physics teachers might call it the distance graph. if you're like me, if you're not very physics minded, if you're like, hey, I just need the math, I need to think it through, then what I tend to do is I tend to look at that derivative number line like we do up above. I know that the derivative function is 0 at, I'll put it here, is 0 at 2. And notice the derivative function goes from below, so negative, to above, so positive, from before and after 2. So what that tells me about the original function is the original function must go from decreasing to increasing at x equals 2. Now, I know the change happens at x equals 2, but I don't know at 2 comma what. Maybe the change happens at the point 2, 1. If it happens at 2, 1, you could say, okay, I'm decreasing before that point and increasing after that point. But I don't know for sure it was 2, 1. Maybe it was at 2, negative 4. Maybe that's the point where it changes from decreasing to increasing. Maybe it happened right here at 2, 0 when it changed from decreasing to increasing. So there are a lot of possible solutions I could draw for the original function, but do you see that they're all going to look like a parabola? The only difference is going to be they might be a vertical translation. So, maybe you drew it up here, maybe you drew it down here. They're all going to be a parabola, just vertically translated one from the other. And you don't have to draw all of those, you only have to draw one, but I wanted you to see there are multiple possible answers. Does that make sense big picture to you? If the original function is a parabola, does it make sense that the derivative would be a line? Well, if it's a parabola, isn't that some form of an x squared graph? And if it's a line, I mean, for all we know, that might be the graph of 2x. So hopefully it kind of makes sense that one was a parabola and one was a line. Okay, look at, we'll call this next one number 2. So again, for me, it's helpful to kind of think through the number line. So I know that my derivative, it equals 0 at 0 and 1. 0 and 1. And I can tell that this derivative, it was above, so the derivative was positive. Then it went below, so the derivative was negative. And then it went back above, so the derivative was positive. And what that tells me about my original function is that it's going from increasing to decreasing to increasing. So at x equals 0, I don't know where, where along that vertical translation, I'll say right here, the original function goes from increasing to decreasing. And then at 1, I decreased too much, sorry. And then, so I'm decreasing towards 1. And then at 1, I turn and I'm increasing again. So maybe a rough sketch might be something like that. Okay. Again, it might be vertically translated from there, but does it make sense that if the derivative is a parabola, that the original might look kind of like a cubic? Hopefully that kind of fits. Okay. Can you go the other direction? So look down here. I'll call this one number 3. This is saying, what if I give you the graph of the original function, or you physics people, they're saying, hey, this is a position graph. Can you draw the derivative and the first derivative and the second derivative? So physics people, can you draw the velocity graph? And then can you draw the acceleration graph? So just to kind of, for you physics people to help you out, first derivative is like the velocity, second derivative is like the acceleration. So let's do one at a time. Let's talk about the first derivative. So again, if it's hard for you to picture, if you don't need this number line, great, don't draw it. But if you're like me, and at first you might need this number line, so this time I'm going to create a number line for my original function. But I'm not looking to see if the original function is positive or negative. I'm looking to see if the original function is increasing or decreasing. And isn't the original function increasing all the way across? So what that tells me is that the derivative is going to be positive all the way across. Well, if the derivative is positive, that means it has to always be above the x-axis. So it can't be a line because at some point it would cross below. It can't be a curve because at some point it would cross below. Well, think about it. I mean, this is a line. What is the equation of this line? If it goes through 1 and it appears that it has a slope of 1, wouldn't this line just be x plus 1? If that's the case, then wouldn't the derivative just equal 1? So just a horizontal line at 1. So there's my derivative graph. And let's go a step further. If f prime of x equals 1, f prime of x, let me write that in there, sorry. If f prime of x equals 1, then what is the second derivative? Well, what's the derivative of 1? Isn't it 0? So the second derivative is just a horizontal line right here at 0. So again, for you physics people, you're saying this is my position, this is my velocity, and this is my acceleration. Okay, if you're not physics and you're not looking at this kind of stuff at all, don't worry about those words, position, velocity, acceleration. That's going to come for us later. Right now, you're just comparing the graph of the original to the derivative to the second derivative. Okay, so let's look at our number 4 right here. Here's what I can see. I can tell that my original function goes from increasing to decreasing, and it changes like right in here. I don't know, what do you want to call that? We'll call that negative, how about if I call it negative 0.2, doesn't matter. So that's where my original function goes from increasing to decreasing, and then it decreases until I get to about right here. I'll call that 1.5, when it changes to increase again. So what that means about my original function is that it's going from positive, meaning below the x-axis, to, I'm sorry, above the x-axis, to negative, meaning below, to positive. So at negative 0.2, we'll say right in here, that's when the derivative graph went from above to below. And it stays below until I get to 1.5. So it stays below until I get to 1.5. And at 1.5, it goes back above. Well, to me, that kind of makes sense, because if the original function, there's my derivative, if the original function looks somewhat like a cubic, does it make sense that the derivative would be a squared parabola? And if you go a step further, the second derivative, if the first derivative is a parabola, if it's a squared term, doesn't that mean that the second derivative is going to be a line, because it's just going to be an x to the first term? So how do I know where the line for my second derivative crosses over? Well, look here. The first derivative equals 0 right here, right? That's where the first derivative, the first derivative has a horizontal tangent line, right? Doesn't that mean that its slope is 0? And isn't its slope the second derivative? So the second derivative must be 0 right here. And notice that first derivative over to the left of that point is decreasing. That means my second derivative is below. And then my first derivative switches to increasing. Doesn't that mean that its derivative is positive? So again, this is hard to pick up a lot of times, and we're going to do a lot of practice with this. So if this is still, kind of confusing, don't worry about it. Just do your best. We'll just keep practicing that. Okay. The homework is going to focus on what we did in the previous example up here, where you find your second derivative information. But I want to point something out, because notice the homework, it doesn't just say to do the second derivative. It says for each of the following, look at A, B, C, and D. Isn't that what we did in 3.3? First derivative, the critical numbers, intervals where the function is increasing or decreasing. And then when you get to letter E, that's where we go into the second derivative and the concavity and the points of inflection. So that's the new stuff. And then what I want you to try is, could you put that all together and actually try and sketch the graph? Okay, so you're doing a lot of information for one problem. Notice I give you a half a page to do it. I know that's a lot, but you'll notice there's only 4 of those. Okay, so even if you can't put it together and get the graph, get as much of the computational stuff, the first derivative and the second derivative and the, the critical numbers and the relative extrema and so on as you can for all 4 of those. And it's not until you get to that next page where you start to think through, hey, can you sketch the graph? So, try those. And then notice when you get down here to the next part, they are calculator questions. So you don't have to do any of the stuff by hand. You can look at the graph of the second derivative to find out when it changes sign, right? Because isn't that when the original is going to have a point of inflection? So you let your calculator do all the work and you just give some answers and some context on those last problems. All right. So the homework is 2.4, and that'll be due next class.